connected? You? Okay. Okay, just checking if it's working. Okay. Rashil, can you?
It's off, it's off, it's off.
Okay.
It's on airplane mode.
I just start myself.
When you're on start, there's just one thing. Start and close it. It's still there, okay?
Okay.
Okay, ready?
Yes. Okay, so I think I'm ready. Oh. Yeah, I think it's working. Okay. Everything's fine? Okay. So with that, hello everyone and welcome to my solutions about this year's 9th problem, the magnetic assist. Let's directly start with the task. The task states attach one or two magnets to a non-magnetic and non-conductive base, such as they attract a magnet suspended from a string. Investigate how the motion of the moving magnet depends on the relevant parameters. So the task specifically tells us that we have to use a string attracting magnets and a magnetic and a dielectric material on the bottom side. And I brought some videos with me to demonstrate how this can look like. We can see several types of motions, one motion between the magnet position and also one motion only above one magnet position. Further on, the task tells us that we specifically have to investigate the relevant parameters affecting the motion. For the relevant parameters, we have the pendulum properties, being the string length and the starting conditions, and the magnet properties being the position and the strength of the magnet. Further going on, for the magnet motion, we have the frequency, the fixed points and the attractors, the patterns and the trajectories which will be investigated. Now, starting with the qualitative explanation, we first have a look at the normal harmonic damped oscillator, which comes to rest at its energetical minima given by gravity. Now, if we ever add a magnet to the system, due to the interacting magnetic fields, there's an additional force pulling the magnet to the bottom magnet, and also on torque, aligning the magnet in the magnetic B field, then causing different types of motion. And then for the resting position, the magnet then comes to the rest at its additional resting position due to the potential minima by the magnetic field. So now for our overview, we will start with the experimental, then the quantitative model. Then we have a look at my results for both 1 and 2 magnets, and then we will draw a conclusion. So now for the setup, we used on the bottom side electromagnets in order to vary the strength. Above we had a paper plane with a cord in the system. Then we had a suspended pendulum from a plexiglass plane, and ring light and an imaging system on top in order to film the motion, which looks like this. And then we had the starting fixture in order to ensure our starting conditions. Then we used OpenCV auto tracking in order to track the motion of the pendulum, where we then track both positions on the outside of the magnet, being color based, and then also accounting for an optical error in our system. So now to the equations of motions and the quantitative theory part, we have those two differential equations for the motions from theta and phi being the spatial angles, where you have the force components in theta and phi direction and also in spatial damping. Those components we get by transforming the magnet into tangential space with these two rotation matches. And then we get the forces in theta and phi direction just as in x and y components of our total force. For our tilting motions, we can also derive a simple differential equation where for our tilt we defined two additional angles, but considering that the change of the angles due to the way greater amplitude order of magnitude is on a smaller time scale than actually on the spatial motions, we here use an adiabatic solution. Now, also describing the total force and total torque in our system. For the total force, we have the gravitational force, the magnetic force, and for the total torque, we have the gravitational torque, the centrifugal torque, and the magnetic torque. Now, for the magnetic torque and magnetic forces, we both have to model our magnets. For the modeling of the electromagnets, we use the Biot-Savart law, where we can just integrate along the parametrization of our electromagnet using an helix, and then we can solve numerically for the B flux field of the magnet. For the modeling of the permanent magnet, we assume that the all invisible spins in this permanent magnet sums up to one to one large spin, and the magnetization is in normal direction of the plane. And then using this given parameterization for our permanent magnet, we can then also apply Biot-Savart law in order to calculate the B-flux field of our permanent magnet. Now further moving on to some independent measurements needed in order to fulfill this theory. We have both the spatial damping coefficient, which we get by tracking a free motion without any magnetic interaction, as you can see down here. And then for the magnetization, we're using a Hall sound and laser distance meter in order to measure the flux density field around our permanent magnet, and then fitting our Biot-Savart law, as you can see there, down there, in order to get our magnetization. Now with that, we can all simulate this within Runge-Kutta fourth method in order to then derive the trajectories of our pendulum. So now, starting with the results. We first have the results for one magnet, where we can see that in the beginning of this trajectory, the pendulum oscillates about its center position, then later on shifting to the position of the resting positions, and we can generally see that the regression of amplitude agrees both on theory and experiment. Further on, we see that here the phi direction stays constant. Note that those are just positive and minus 180 degrees, so it's just the same as 0. Now, further investigating this motion onto these spectrograms, where we look at the frequency over time, where we can see from our spectrogram analysis, we can see that we have a first phase with mostly constant frequencies, then an increasing frequency in another phase, and then again it stabilizes in the last phase. This also gets predicted by our theory, where we can see that generally trend-wise this agrees, and we can divide this into 3 phases. One, the first phase, as I already told, with a constant frequency, then a second phase with a rising frequency, and then again a third phase with an almost constant frequency. Looking at the phase spaces of those phases, we can see that in the first phase we have an ingoing elliptical in the phase space, which generally speaks for a damped oscillator, since in this case, due to the high distance between the magnets, so the upper and the lower magnet, one can assume that generally this is a gravitational dominated phase, since the energy of the pendulum is still very high. We can check this by looking at the frequencies for various parameters and then comparing it to just the solution of a simple harmonic oscillator. As you can see right there, this agrees very well. So one can say that this is the gravitationally dominated phase, and this behaves like a harmonic oscillator for this phase. Then for a second phase, we see that we have a transient phase here, where we have those attractors in the center, but still the ingoing effect from the gravitational phase is there. And then when the pendulum loses some more energy, we have this ingoing elliptical. Again, in this case, the magnetically dominated phase, which we can also check by the frequencies, approximating this to be a quadratic potential. And then doing a magnetic force approximation only being dependent on the distance. We can then linearize this ODE and compare it to our measurements, where we can actually see that this analytical model agrees. So we can see that generally this is the magnetic dominated phase, and also our numerical model again agrees here very well for the frequencies. And again, this phase then behaves like an harmonic oscillator. So now for the resting positions, we have investigated several resting positions, seeing that with one magnet we can achieve up to 2 stable equilibrium points. And looking at the resting positions over some different parameters, we can see here that the magnet just moves along with the position of the magnet, and increasing the current at the bottom magnet, we can see that the magnet moves closer to the magnets themselves, but we can also see this case here, when the magnet is too far away, then actually it rests at the different stable equilibrium. Now, coming to the same for two magnets, where we can again see the trajectories with the same two phases as before. Again, looking at the frequencies over time, we can again see this first phase, where this downgoing trend caused by the deflection and then having longer periods of time. The second phase rapidly increasing the frequency due to the magnetic interaction, and then the third phase with a nearly constant frequency as well. Those we can see that generally we have the same 3 phases as in with one magnet. Now looking at the trajectories in a top view, both comparing experiment and theory, one can see that they qualitatively agree quite good, and we can see that in the first phase we only have a deflection of this linear motion, as both shown in experiment and theory. Then in the second phase, the pendulum moves between the position of those two magnets. And then when the energy of the pendulum drops, it can't escape one potential energy minima anymore, and then only oscillates above one of those magnet, where it then comes to rest. Again, here looking at the resting positions, where we can see that with two magnets, if we move them far enough away, we can see that we have up to 3 stable equilibrium positions. Which we also investigated both experimentally and theoretically, where we can see again that with generally the magnet moves along with the position of the bottom magnet. But again, we have those cases where within a magnet being too weak or too far away, when looking at those potential energy maps, we see that there's no stable equilibrium anymore, and the magnet then comes to rest at another potential energy minimum. But generally we can say that the magnet just moves along with the position of the closer bottom magnet. Now, these resting positions can also be investigated using the fractal basins of attraction, where we plot the resting positions. So we also, for every point we simulate, and then we check if it rests at the blue magnet or at the red magnet. And generally we can see that we actually have here fractal dimensions, and we can see that we have here a low sensitive regime, where what we can check about with the Lyapunov exponent, which is when it's negative, calling a convergent in the phase space, and positive being a divergence in the phase space, so talking for chaotic behavior. And we actually checked here for a negative Lyapunov exponent in this basin, which we can see that in the first phases it stays, the path doesn't change pretty much. In the outer regions, we have a high sensitive regime, actually causing some chaotic behavior, which we can see for different parameters. And then for the task fulfillment, we both did experiment and theory-wise investigated the motion on frequency, fixed points, patterns, and trajectories. Thank you very much for your attention.
Thank you, reporter. So firstly, did you model the tilt of the magnet in your theoretical model?
As I stated, we modeled the tilt with 2 tilt angles we defined.
Okay, so did you model the resistance of the... So just to clarify, your model does include the tilt angle, right? So you were able to plot the tilt angle with as time goes on.
No, we modeled the tilt with 2 independent angles, being to the normal position of the string, and then the magnet tilts and aligns with the magnetic flux density, as I showed in the report, with an adiabatic solution.
Thank you. Okay, so what's the distance between your top magnet and your bottom magnet? What's the closest distance?
The closest distance was like about 7 centimeters or something like that, I think.
Okay, thank you. So your damping model only assumes air resistance, correct?
It assumes spatial damping as in a linearized equation of motion shown.
Okay. Thank you. So slide 68, how do you get the error bars in that slide?
68. Okay. I think needs a bit time. Some few animations. 68. You mean those error bars?
Yes.
Which ones? In which direction?
Both, please.
So, okay, for this string length, we measured it with a ruler, and we have like of 1 millimeter accuracy, and then the half of that is only we can measure. Then for the current of the bottom magnet, this varied a bit over time, so we tracked that and took the mean out of that, which is then the error in the current at the bottom magnet for all of our measurements. And for the frequency itself, we have a tracking error, but I think there's some lot of more errors accounting in this additional error we
Thank
can
you.
talk about later.
So slide 87, how do you get this graph?
80. Okay.
Okay,
We
thank
can
you.
discuss about this later.
Okay, so good afternoon, everyone. I'm Duanyu, and today I'll be opposing problem number 9, magnetic assist. So first, a summary of the report. The reporter firstly quantitatively explained the motion using the potential energy wells. He then modeled the magnets as current cylinders and modeled the spatial and twisting motion of the pendulum. He varied the base magnet count, the base magnet positions, and the initial conditions of the magnet, and lastly, analyzed the pendulum's motion in different regimes. So move on to the strength of the report. Firstly, I believe that the report has a good experimental setup. So they use an overhead camera to track the motion of the magnet, and they use color-based magnet tracking, which I believe is more accurate than, for example, hand tracking it. They also use perspective transform to account for the optical error in the camera, which is important given that the camera they use was put relatively close to the magnet, and this accounts for the parallax error. Next, they also varied many parameters such as the base magnet count, position, and the initial conditions, and they obtained the basing of attraction for two base magnets, and I believe this is very important because with two base magnets, you expect chaotic motion, and this can be easily visualized with a basing of attraction where you can see where the motion gets chaotic. Lastly, they also used an analytical model for low energy magnet motion, and I believe that this will contribute to a good qualitative understanding of the magnets, the top magnets motion in such a case. So now I'll move on to the areas of improvement of the report. So first, I believe there was an inadequate assumption for the twisting of the magnet. So from what I can understand, the reporter's report has an adiabatic assumption due to the different time scales of the magnet. So what he did was that he assumes that the tilting motion of the magnet is instantaneous. And I believe that this is not really correct because at very low magnetic fields, so for example, let's say the magnet is very far away from, so the top magnet is very far away from the base magnet, then obviously the tilting would not happen because the string has some resistance to this tilting, and the magnetic torque is too weak because it's too far away. And I believe that this would break his assumption that it is adiabatic and that it instantly aligns with the magnetic field. Furthermore, I believe that one thing he didn't want to do is the twisting dissipation. So I believe the key damping in this problem would be the shear forces within the string as a magnet twist. And I believe this is more significant than the air drag, and that without this force and with only air drag, you would not be able to, with this twisting dissipation, the damping will be a lot higher than simply air drag. Lastly, there was also insufficient experimental verification. So okay, so first for the position time evolution, I believe that the graph was too zoomed out, so we cannot really accurately see, for example, if the period is correct, and we can only see the decay envelope of the motion. And for the basing of attraction, I believe you could have experimentally verified this as well as the Lyapunov exponent. There's also an incorrect implementation of the Lyapunov exponent. So I believe the Lyapunov exponent may not be very correct because it should be linear fitted within the first few sections of the divergence, and then it should taper out. So yeah, so I don't see the part where it tapers out, so I'm not quite sure if this is correct. When the state space gets saturated, it should taper out. So I would like to discuss this later. And lastly, I believe that he could have investigated the deflection of the pendulum about the base magnet because this problem is about magnetic assist, and I believe it's similar to something like gravitational assist, where you have some deflection angle, and I believe that he could have investigated this phenomenon, and I believe that it could have been interesting if he had discussed it. So now I would like to move on to the discussion. So first, let's talk about the dynamic modeling of the tilt angle. So do you agree with me that, so let's say, so just to clarify first, let's say this is your base magnet, yes, and this is your pendulum magnet. So in your theory, you assume that the magnet tilts towards the base magnet instantaneously. Is that correct?
Not so in the simulation it is instantaneously due to the adiabatic solution, but just for a certain range of force.
So how do you determine this range of force which it tilts? Because do you agree that at very high, for example, this is very far away, then it wouldn't even tilt because tilt angle is extremely huge.
So the range of force was approximated by using one solution with the full solution, but since this took very long and would not have produced these results, we then changed because we saw that at a certain point the change of the tilting angle was not way greater by orders of magnitude than the change of spatial amping, and at that certain point, this is the definition in the force range we took. And also, we had very small starting angles, and therefore I think this assumption is applicable.
I'm not quite sure I understand what you mean. So do you mean that, so you're saying...
I can explain it to you again if this clears it up. So what we done a whole simulation with all four ODEs being solved coupled, and what we checked is when the change of the tilting angle is not way greater by orders of magnitude than the change of spatial amping. So when they're about the same, then we said this is the range where we can then model this tilting adiabatically, since it happens on the time scale about 3 orders of magnitude higher.
Okay,
as
okay.
I showed in my presentation.
So you're saying that, so you did a full simulation and you notice that, for example, at this point, this tilt angle is not really significant. So that's when you say that, okay, so this is the range at which it doesn't matter anymore. Is that correct? Okay, so, okay, so now that we've cleared that up, I still want to discuss, so for your current model, so that for a current model at very small, when the magnet is very close to the base magnet, you still have this adiabatic assumption that it turns instantly, right? But I don't think that is the case, because first, the string has some resistance to turning. It wouldn't turn instantly, right? And this, I believe this angle is quite large. And as a result, it wouldn't fully turn to the adiabatic solution as you suggested when it's quite close to the base magnet.
So can you clarify shortly what resistance you mean? And I would still think that is actually applicable because we checked for the orders of magnitude being greater than about being around greater than 3 orders of magnitude, and therefore, in order to get to our simulation in a certain time, we then took this adiabatic solution. As a simplification, we actually think is justified. So this was just a simplification we had to make in order to solve the theory. So therefore, yeah.
Okay, well, okay, I guess we'll have to agree to disagree on this. So the string damping, the resistance I'm talking about is that, for example, if you just hold a string out like this.
Sorry, so I agree with you that it is actually relevant, but we needed to do the simplification in order to solve the theory, and I would still think that this justification within the range of error is actually applicable because the order of magnitude, as I already stated multiple times, is much higher.
Well, I think one way you could check, you could perhaps plot the period against plot the period against, for example, like you can check the period when you have the all degrees of freedom and we don't have all the degrees of freedom, and perhaps you can see if there's a large deviation in your theory. Okay, but anyway, I'd like to move on to the next point here. So next, let's talk about the Lyapunov exponent. So you have here. Yes. So I'm not quite sure if this is correct because normally for a Lyapunov exponent, you would expect, for example, a straight line followed by a part where it tapers off. But I don't see that here. Could you clarify why?
Okay, so what this plot is essentially, we start at a certain point. In this case, it was at 10 minus 10. And then with about 100 iteration points or something, I'm not really sure what value exactly it was, but something in that range, we then within small distance around this point, then checked for the, so simulated the different trajectories, and then checked for the divergence in the phase space over time. Which actually looks similar to what this literature presents. And I'm not sure of what linear you are talking about. This linear fit is just the linear fit in the logarithmic scale in order to present the exponential divergence in phase space, talking for this actually chaotic behavior we have in the system.
Okay, thank you. So maybe I can elaborate more on this. So here you're plotting the log scale of the deviation. Yes. Against the time. Okay, yes. So here, in the Lyapunov exponent in chaos, you assume that the deviation between the trajectories is exponential. So that's what it implies, and this will imply a straight line on this graph, which is what you have shown here. But for this part of the graph, this part, which is basically a straight line, implies that it has reached a maximum width of the deviation. So the two trajectory has drifted so far apart, they can't drift like more far apart anymore because they have deviated enough. Okay. So to get an accurate Lyapunov exponent, what you usually have to do is you fit a straight line to the first part of the curve.
So I need to clarify this for you because what you're essentially talking about is when the divergence then actually comes to rest, and the divergence limits itself due to the different attractors we actually can see in the system right here. But in my case, this is for about 90 seconds. So this is like 30 seconds. This is still within the range of the first two phases as I presented in my report. And therefore, I would agree with you that at some point the divergence stabilizes due to the divergence being then limited to those fixed points we can see in the fractal basins of attraction. But therefore, we actually don't disagree here It's just another way to show, and it's just because it's limited to 30 seconds in this case. Also for a reasonable time in solution, because we simulated about 200 or 300 simulations, and didn't want them to always go till 90 or 100 seconds, just for time reasons.
Okay, so your
But-
whole motion is about 90 seconds.
My magnet, as I already showed in my trajectories, comes to an rest at from varying different measurements to around 90%. If
Okay.
this clears your question up about
Right.
the Lyapunov exponent.
Okay, well, I think that you could potentially experimentally verify the Lyapunov exponent to see if this theoretical calculation is
So,
applicable. So you could, for example, take a lot of set of data, and some of them will end up being similar. And you
I'm
can
sorry.
track their deviation over time.
I'm sorry, I have to disagree with you there, because experimentally verifying your Lyapunov exponent in this system is essentially very hard, because when starting at at one point, I think the deviation you need, so this is like deviation of 10 to the -8, the deviation you need in order to then actually calculate the divergence in the phase space being reasonable is not within our errors we have in our system. So therefore I think it's not actually justified to say that one should have investigated the Lyapunov exponent experimentally, because the data is just too, how you say it, too errorly in order to actually then get the divergence in the phase space for multiple trajectories, and also the effort you have to put in order to track multiple,
Okay.
so hundreds of trajectories. It's
Okay, sir.
just a bit too
Sorry to
much.
interrupt, but I'd like to move to the next point. So I disagree with you. I believe you can do estimate it, but let's move to the next point. So let's look at the experimental verification. So can you go to your position time graph in this report?
What?
So your
Oh, sorry.
Yep.
It's not working. You mean, okay, this froze. Okay, sure. You mean with one or two magnets? This
With,
one?
uh,
Oh.
with
it's
one
disconnected.
magnet, I believe.
I'm sorry. I can't connect it anymore. Maybe we can shortly pause. If it's possible. Is the... Okay. But generally, do you mean with one or two magnets?
One.
With one magnet, sure. But it generally doesn't seem to work. Yeah, I already.
Well,
Yeah,
I want to make sure I look at the
Okay,
correct graph first.
I can log in your
Sure.
if this helps.
Sorry. Yes, I think this graph.
Yes, you mean this one? Okay, I think I'm logged in again.
Oh, yes. So if you look at the top graph there,
Yes.
okay, the just top graph, I can see that your theory is slightly offset to the top apart from the from the experimental. Could you explain why that happens?
So I assume that to be because of we have a slide with the tilting motion for outer parts. So here the magnet is very far away, and when it gets close to the magnet in the actual experiments, you can see that it moves along very easily due to some imperfections in the magnetic. So how you can explain it? So the
Okay, thank you. So, in conclusion, we discussed the adiabatic assumption, and the tilting happens instantaneously. While the reporter and I agree that it is relevant to the modeling, I disagree that the assumption is valid due to its effects on the dissipation of the string. I also suggested to check the deviation in the period of the magnet to verify or disprove their assumption. And at the last point, the reporter also mentioned there's some deviation in the graph due to this assumption, so I believe it may not be that valid. We then discussed the Lyapunov exponent, and I said that I believe it would taper off. And the reporter and I agree that it would taper, but the reporter said it is not seen due to the short time scale of the motion. I suggested we can experimentally verify the Lyapunov exponent by taking similar trajectories, and the reporter and I disagreed on whether this can be done, and I believe it to be relevant. And for the last point, we clarified that it is due to the adiabatic assumption. So I don't think the reporter has fully answered the problem statement because he has neglected the tilt angle of the magnet, which is essential to the problem, as it says a string which implies that there has to be some tilt angle present. Thank you.
Okay, it's on. So first of all, to the reporter, it seemed that your spectrogram had a lot of noise. Can you clarify what dimension you used to calculate the spectrogram? Did you use theta, phi, or Cartesian coordinate?
We used theta. It's the
Okay.
theta data.
I see. So I'd actually recommend increasing your FFT bin width because like your time resolution seems very low for the frequency, and that seemed to show on your plot. So to the opponent, do you think that there were any issues with how he calculated the potential hose in theory? Do you think that there were any issues with how he calculated the potential energy for the potential hose? Okay. So to the reporter, can I confirm that you used a magnetic dipole moment to calculate the potential energy of the magnet?
No, I didn't.
It seemed that you used B field.
Sorry, I didn't
dot.
use a dipole moment.
It's okay.
Absorption.
Maybe we can go to a slide. I think that you used B dot dipole moment
Which slide exactly do you mean?
for your equation to calculate the potential hose.
This one?
Uh,
This is just the added potential.
so how did you calculate the potential of the magnet?
The potential of the magnet is just due to the you have the B field and you have the B field and the
Dipole moment?
The magnetic
Okay,
dipole
so
moment. So it's not.
It seems that you are using the dipole approximation to calculate.
No,
since
I
using the
didn't.
dipole moment.
You get the dipole moment from the magnetization.
Yes, but that's a dipole approximation. I'd recommend using a force integral of your Lorentz force.
No, it's not.
Is it not?
It's,
Okay,
no,
wait,
it's not a
maybe-
dipole approximation.
we can
The
move it, yeah.
dipole was determined with the Biot-Savart law.
Okay, sure.
in
We can
order to
maybe
clarify this.
disagree on that. So on slide 75, you mentioned that deflection caused a decrease in frequency. So you'll create a spectrogram for your two
Which
magnet
slide?
case.
Sorry.
Slide number 75. So you see a decrease in frequency here. I want to ask, did you verify this with any other data? Because this spectrogram looks very noisy, so I'm not too sure.
I haven't plotted it with. I haven't compared it with much more.
Okay, so this is a
data.
single trial of a simulation.
This is a single trial of the simulation.
Okay, I
yes.
think it would be very important to take more, at least like do more theoretical simulations to get a more accurate frequency for the two magnet case, because this doesn't make much sense to me. So to the opponent, what do you think the effect of the magnet orientation simplification that the reporter used is? So how much error do you think that induced, and what type of error?
Of the magnet.
Yes, exactly. Yes.
Well, I believe because there's a magnetic force, there will always be some error with respect to the tilt. And I think.
So do you think that, sorry to cut in, do you think that the reporter's assumption that the magnet's always oriented along the B field due to the dipole moment is incorrect?
I believe it's incorrect because the string has some resistance to bending. It doesn't bend with no force. It bends with some.
So that's good to hear. Thank you.
Go to the first slide. Times 3, 2.
This is not your laptop. No worries.
Wait, let's go.
Sure. So I'm Luyu from Team Canada, and today I'm reviewing magnetic assist. So I won't read through a question statement since that's already been read. So we identified some key tasks for this problem. First of all, to create an experimental setup. We think that that was well done, and the camera tracking was quite ingenious. The second task was to produce an equation of motion taking into account all major factors. We believe that this was somewhat satisfied. However, the orientation is very important, and that was not quantified. Task number 3 was to identify quantification of motion. So I think that there was some interesting use of frequency analysis to investigate the motion. However, there could be more quantification of the 3 phases that the reporter mentioned. And lastly, to compare theory and experiment to the extent possible. And I think that this was really lacking. A lot of the comparisons had single trials, or the theory was a single trial, which was unsatisfactory. So for a summary of the report, they did differential equations of the magnetic bob to find the equation of motion. They did some torque equations, however, that was limited. And for the experimental confirmation, they created a basic camera tracking, which I detailed previously. So for the merits of this, they somewhat detailed all of the forces. However, they missed things such as the eddy current damping, and the damping forces weren't very well presented in general. Secondly, the experiment itself was well built, as I've mentioned. The numerical model was clear, and the use of potential hills for visualization was interesting. However, there are issues with that, which I'll get to in a second. So for the possible next steps, I realized that the magnet characterization had very few data points. They were not on the fit curve, including, and the error bars were very large. So I'd recommend more data points and hopefully a more precise magnetic field meter. And secondly, I'd recommend using Cartesian coordinates for plots. I don't know if you realized, but for one of the plots, it was non-continuous because you're using the spherical coordinates. And so I'd recommend converting those to Cartesian coordinates so you can more easily view the data. 3, the time management, you didn't manage to complete your report. And 4, there was very limited non-frequency analysis. So there was a single graph showing a comparison of the motion between the theory and the experiment. And as the opponent correctly pointed out, that was actually not aligned very well with the experiment. So I'd really like to see more trials as well as quantified error analysis, such as root mean square error. So for the summary of the opposition, they had some very good key insights. So they talked about the dynamic modeling of the tilt angle, which I agree is very important. They talked about how dampening did not consider the transient twisting dissipation within the swing, which is also very important. And they talked about the incorrect implementation of Lyapunov exponent and lacking experimental verification. All of the points which I agree with for there. So for possible next steps for the opponents, so the deflection of the magnet was explored with U-hose. However, so actually, the deflection of magnet was explored, unlike what the opponent said. However, it's not very relevant. The magnetic assist that you mentioned, so the gravity assist, I don't believe it's very relevant to the problem since it asks for us to investigate motion. So I think the reporter was actually fine there. For the second part, they missed a point about the potential hills using the dipole model. So once again, the dipole model is taking the dot product of the magnetic field and the dipole moment. For 3, they missed the effect of eddy currents, which are quite important to the problem. And 4, they could have investigated more parts of the report. So for the discussion analysis, firstly, they talked a lot about the lack of simulation for a tilt of the magnet, so the relevant torques of the system. So the opponent said that should be solved in the numerical simulation, and it is possible. And the reporter's response was that it's irrelevant in large theta angles, while at small theta angles, the magnetic dipole torque holds true. And our own opinion here is that the reporter is correct that the approximation of dipole torque is dominant. However, axial twisting of the string is incredibly important to a phenomenon, as it can hold a lot of energy in some parts of the motion. Next up, they also talked about the Lyapunov's exponent, and here the opponent raised the point about the reporter incorrectly calculating the Lyapunov's exponent. The reporter's response was that it was a bit confused, but I think that they said there was linear fit of the log plot. And we actually think here that the most important lacking part of this was that they did not average many cases for the Lyapunov's exponent. That's crucial for calculating it, and they didn't vary the degrees of freedom either, as they should be investigating all of the degrees of freedom of the system. Thank you.
So there's a bit to remark. So we took the maximum Lyapunov exponent, which is generally a normal idea. Then also, also for the dipole moment, I never mentioned that I'm using a dipole approximation. We determined the dipole moment, as I already stated, with independent measurements from our Biot-Savart law. Also, the reviewer mentioned that I'm sorry. Also, the opponent mentioned that the Lyapunov exponent was not right, but however, we think that this is actually just the first part, which was a misunderstanding. Also, I never stated that the deviations from the theory in the distance over time graph comes from the tilting. It's from the tilted axis of the magnetization, which is just an imperfection in the magnets, which causes this deviation, which we also had an appendix slide further on. Also, the opponent stated that our experimental and theory comparison was only due to position over time, the Bazins and the Lupinov. However, we showed frequency over time, frequency over different parameters. We showed the resting positions over different parameters, and therefore also the reviewer said that the theory and experimental comparison was not quantified enough. I would disagree here. I think I showed the resting positions as well as the frequencies for various parameters in order to give a qualitative understanding of the physics behind. I showed the frequency over time, the distance over time, and the phase spaces in different phases for one example, for both 1 and 2 magnets, in order to understand the physics there behind. So therefore I would disagree that the quantitative comparison is lacking, and thank you very much for this pleasant fight and your great questions.
Thank you very much. Could I ask the reporter to leave it connected?
Yes.
Just in time. Then we have 5 minutes for jury questions.
Sorry.
Who wants to go first? Yeah, Becca, sure.
I want to ask reviewer first. So you mentioned the tilt angle, and you said it will be relevant for which angles? The big vertical angles or the small vertical angles?
The axial spin, so along the spring axis, the string axis. So you need the torque calculations to be able to calculate that. But I think that the reporter's approximation of the magnet following the orientation of the magnetic field is good for the general motion of the magnet. But it misses some field.
Okay.
I have a question to the to the reporter on the spectrogram plots.
Yes.
What is the reproducibility of these frequency diagrams, and also like the sensitivity of initial conditions? Or, like, for which situation do I see this here, basically?
So this is so the general trend is for every case with 2 magnets, where we have this first phase where it's decreasing because the pendulum motion gets deflected. Therefore, it's a longer path, and therefore the period time increases, which causes the frequency, of course, to decrease. Then we have a second phase where it increases.
Yeah, I understand that, but this is just a random initial condition, and you recorded the motion.
No,
or
it's
is
the same initial conditions as in the others, where the magnet is positioned here with -5 and 3. So it's one example I used to take the trajectories, the phase space, and the frequency, if that wasn't cleared up, in order to explain the motion on various.
So you picked one starting
points.
position and looked the frequency for that, for this spectrogram?
Yes, for this spectrogram, yes.
Okay. Anybody first give the other 3 a chance if they have a question? Okay.
Can you go to slide 68?
68, sure. This one?
Yes, here. So on x-axis you have the strength, the length, right? Why is it taken like with the different ranges? Because like you have one very big, then
Yes.
experimentally
Okay,
very small.
what
Does it have
Okay.
physical sequence?
What we did is we essentially varied those, and then we had those measurements, and we wanted to, so we always kept the distance for the starting angle constant, and then we changed the length, and then this was in case where we are not in the small angle approximation in order to see actually this deviation, so I can clarify on that. So this was just an additional measurement on the DDRs.
No question, I will ask.
But maybe just on this, it came to mind that initial conditions is not in XY coordinates, not in theta coordinates. It will vary string length. Or how did you were
Okay. The initial conditions were in XY coordinates, so we had like this fixing device which I showed in the experiment.
length, the theta changes.
So- Yes.
Can you go to either 77, 78, or 79? I just want to know that you compared those trajectories You didn't put them in the same graph, so why is it not comparable
this is
quantitatively?
this is just for-
Qualitatively, we can see.
This is just for visual reasons because there's so many lines if you put them over together, but it's the same trajectory as showed before. And therefore, I just wanted to qualitatively give a view on how this motion looks like from the top view, because I think this is crucial when talking about the motion to actually see it from top-wise.
Could you go to slide 56?
56.
I think you can type actually the number.
Sure. Sorry. I think PowerPoint is a bit lacking. Yes, this graph.
So there the magnet is at 2,5 because the equilibrium position is not at theta equals 0 to which it converges.
No, theta 0 is just the center position, and over time the magnet then comes to a rest at a tilted position, as you can see right there.
So that's the position of the magnet, right?
This is
And that was always.
It's going towards the position of the magnets.
And did you also compare this for other magnet positions?
Yes, this was essentially the graphs we showed, as we give it short time, for the resting positions. Sorry.
Okay. Yes, I recall. Yes.
Yeah, this were the resting
you.
positions.
We have a 7, a 6, a 6, a 8, and a 7. And next, the grade for the opposition, please. We have an 8, a 6, a 7, a 8, and a 7. And finally, the grade for the review. Sorry. A 6, a 6, a 7, a 8, and a 7. Can I take this? All right, for the report, well, I think Mladen is always on the high side, but we have some general feedback, yeah? On the partial grades?
Yeah, partial grades 5.9, 2.6, overall 8.5 rounded down. I think that it's this is what it explains. I like the way it was. The report considered the tilt component and everything looked pretty, well worked out. I enjoyed the discussion afterwards, but I think that all the main important parts were covered well.
Maybe just a very brief general comment. I think you did a lot, and you have a lot, but I think you almost wanted too much in the presentation. And I think not, or at least to me, it did not always come across clearly what were you doing and why were you doing this. It was a lot of sections of results, but it was not 100% clear, like the ultimate goal. It was more like a sequence of results to me. And I think it could have been improved maybe if you cut part of what you actually had and present less. But we also had a 6.
My thing was I gave the reporter 4 in presentation. The thing is the same thing for me here. And for discussion, I gave 1 because I felt like you had a lot of things in your slides which you could have shown, which would have answered the questions. And I wanted you to show you more of your experiments during the discussion, which was actually, in some points, was actually proof that like your theory was actually right and your assumptions were good. So that's why I gave you 1, 4, and 1, and minus 0 points because you answered questions very well. Yes, and also initial parameters that you had for experiments, and maybe some like pictures of, for example, when you showed the experiment, if you showed like this was the string length was this, the magnet was this, and the parameters, that would have been very good. But still, you had a lot, and I think the time management was the main problem for the report. But I guess it turned out 6. For the opponent, it was like the quick questions I gave you 0.75 because I have 4 or 3 questions were asked only. Then the opposition speech was amazing. I gave you 3.5. It was almost perfect. But the discussion was literally 3 questions were asked. There were so many graphs you could have discussed there, especially the experimental ones, because the opponent had a lot of experiments which would have further been explained. And for the discussion, the discussion is basically the main part where you got like 1.25 out of 4, and that's why the grade turned out 6. But speech was very, very good. Yes, thank you.
Yeah, I fully agree on the speech. It was much better than what you did in the review before. It was really clear why you're saying something is good or bad, and that was really good. The only criticism, I agree with Becca, I mean, I was on the high side with the 8, is the discussion got a bit messy. Like, it was a good start with the tilting, then it got a bit messy with the Lyapunov experiment, and it started to become a bit unstructured, but the summary was perfect. I think we move on to the reviewer, but Mladen, maybe?
1.8, 2.1, 3.0. 7.8, which is a solid 8.
Your scale. Yes, that's the most important. Becca, can I ask you on the review again?
For the review, I gave you 1 in questions, then 1.5, 1.5, and 1.5, and plus 0.5 for introducing the new topics. For example, it was the spectrum noise and so on, which was not mentioned. Okay, again, after the review of report was decent, everything was average, so you got the average points overall. And my question you answered normally, so that's why it's 6. I think what could have been improved is the review of opposition, because opposition was good, review of report could be, a lot of could be taken there from the review of report. And also questions, a lot of questions. And I think questions should have mainly been on experiments, because there were so many of them. And most of the questions were theoretical, so that's why I gave you 1 out of 2.
Are there any questions from the teams? These score sheets are, of course, also uploaded on CC, and the jurors are also here during the break. They're also happy to answer any questions you may have. But I would like to thank you all for a very good fight. Both rounds have been very good so far. So let's have another 10-minute break and reconvene at 20 to 5.